We're going to draw the following compounds with single covalent bonds. These are the compounds that we'll draw shown here, and we're going to look at circling the lone pairs. A lone pair, or lone pairs, are pairs of electrons not shared between atoms. Sometimes we also call these unshared pairs. Let's first take a look at HF, hydrofluoric acid. And our first step is we're going to count how many total electrons we should have. And we're going to do this based on the valence electrons. So we're going to have 1 from hydrogen plus 7 valence electrons from fluorine. So our final dot structure needs to have a total of 8 electrons. So I'm going to track these by using dots and X's depending on which element is bringing in the electrons. And this is just to help you keep track of where things are coming from. So if we have hydrogen's electrons represented by an X, so there's hydrogen's electrons, and we represent fluorine's electrons by dots. There are the 7 electrons that fluorine donated, and there is the 1 electron that hydrogen donated. Let's count the lone pairs. We have 1, 2, 3 lone pairs. This pair here is shared. This is what is the single covalent bond. So we have 3 lone pairs. In this particular molecule. Let's take a look at chlorine fluoride, another molecule. In this case, we have 7 electrons from each of the atoms for a total of 14 electrons. So there's chlorine and the 7 valence electrons, and there's fluorine, and we're going to represent fluorine's electrons with X's just so we can kind of keep track of things. And there's fluorine's 7 valence electrons. When we're done with the structure, each one of the atoms has an octet around it because they both get to count both shared electrons, and there are a total of 6 lone pairs. So let's take a look. We'll go ahead and circle all these lone pairs. The next one we're going to look at is ammonia, NH3. Now let's do H2S. We're going to do this one first. So we're going to do dihydrogen sulfide, H2S. We're going to have 1 valence electron plus a second one from the second hydrogen plus 6 valence electrons from sulfur for a total of 8 valence electrons. So we'll represent the hydrogen electrons with the X's and the sulfur electrons with the dots. We have a total of 8 electrons. Each hydrogen has 2 electrons, so that it is isoelectronic with helium, and sulfur has 8 valence electrons. In this case, we've got 2 lone pairs located, one above the sulfur and one below the sulfur. Now let's try the ammonia, NH3. Here we have 5 electrons from the nitrogen, and then we have 3 electrons coming from each one of the hydrogens. So nitrogen contributes a total of 5 electrons to the molecule, and each hydrogen contributes 1 electron to the molecule. So we have three lone pairs, we have one lone pair and three single covalent bonds. Our last molecule is going to be methane. This is the primary component of natural gas, so CH4. Here we have 4 valence electrons from carbon plus 4 valence electrons from the 4 hydrogens. So carbon has the 4 valence electrons. Each hydrogen contributes 1 valence electron. Notice in this case we have no lone pairs. All of the valence electrons are involved in single covalent bonds. Next we're going to look at sharing 2 pairs of electrons. If we share 2 pairs of electrons, this is called a double covalent bond. To show how this works, let's first look at the diatomic element oxygen. Oxygen has 6 valence electrons. So if we have 2 oxygen molecules, and I'm going to show the second oxygen molecules, I'm going to use X's just so it's a little easier to track what's going on with the electrons. Each one of these has 6 electrons. They need to combine in such a way that each is now going to have a full octet. So here's what your diatomic molecule is going to look like. What we have here are 2 pairs of electrons that are being shared between the 2 oxygens. If we draw a Venn diagram showing the electron sets, you can see that we have 8 electrons around this oxygen, and the second oxygen also has 8 electrons because it gets to count the shared electrons also. So both oxygens have fulfilled the octet rule with 8 electrons, even though we only have a total of 12 electrons in the entire oxygen molecule. Let's take a look at this compound here. This is formaldehyde. And let's take a look at what is happening in this case. We have 4 valence electrons from the oxygen. We have, from the carbon. We have 6 coming from the oxygen and a total of 2 coming from the hydrogen. So we have a total of 12 valence electrons available. Let me show you what the drawing for formaldehyde looks like when we do the dot structures. We have carbon contributing the 4 valence electrons. We have each one of the hydrogens contributing 1 valence electron. And we have oxygen contributing 6 valence electrons. Let's take a look at the Venn diagram now. If we circle all of the electrons that oxygen gets to count as part of its valence shell, we can see that we have 8 electrons. If we do the same thing for carbon, again, we have 8 valence electrons. And if we follow up with hydrogen, we can see that each has 2 valence electrons, so that they are isoelectronic with helium. So each one of them has met the octet rule. Now, notice here on the oxygen that I have drawn these electron pairs together. So in terms of electron pairs, we have 2 lone pairs in this particular molecule. So we have 2 lone pairs. We have 1 lone pair here and another lone pair here. Let's come back and take a look at the number of lone pairs that we had on the oxygen molecule. We have 1, 2, 3, 4. So this one had 4 lone pairs. Last step, we're going to look at sharing 3 pairs of electrons. This is called a triple covalent bond. And the example that we will use is another diatomic molecule, nitrogen. In this case, we're going to have 5 valence electrons from each nitrogen atom. So we're going to have a total of 10 valence electrons that need to be arranged in such a way that each nitrogen has 8 valence electrons. So let's see how this is done. Each nitrogen is going to contribute 5 valence electrons, so there's the first nitrogen. And then the second nitrogen also contributes 5 valence electrons. There is your triple covalent bond where we are sharing 3 pairs of electrons. This nitrogen has the full valence shell, and the second nitrogen also has the full valence shell. And just for fun, let's count the lone pairs. We have 1 lone pair here, we have a second lone pair here, so we have 2 lone pairs. These lone pairs are going to become very important later when we talk about the shapes of molecules.